Hello everyone, this is Lab 5 and we will be discussing the CMOS differential amplifier. Differential amplifiers find a lot of use in analog electronics, so let's try to understand the basics of it with this lab. So the first part of this pre-lab is to determine the Q points. So that's basically just the DC operating point of the amplifier. And in particular, we want to figure out the Q point, or the DC operating point of M1 and M2. What is the VGS values for those guys? And it specifically says to don't neglect body effect on M1 and M2, which will change the threshold voltage. Now we know that this should be about 4 milliamps here based on the previous lab. Our ref is going to be the same as what you used for lab 4 in order to set 4 milliamps in the reference branch, which gets mirrored to the output branch here. So with 4 milliamps, we know 2 milliamps should go to both of these branches if everything is perfectly matched, which is safe to assume. So we know 2 milliamps is the bias current. We know all the transistor parameters. We know he's got to be in saturation for it to work correctly. We can figure out the threshold voltage and VGS with that information. So first, let's write down the saturation equation. So ID 1/2 Kn prime W over L VGS minus VT squared. And you can neglect channel length modulation here to make things a little easier. So they tell you so VG is going to equal 0 volts here. It's equal to 0 volts. We do not know what Vs is though, and we do not know what Vt is equal to. So we have two unknowns. So we write a second equation for the threshold voltage. Vt1 is equal to Vto plus gamma square root 2 phi plus VSB minus square root 2 phi. They give you VTO, they give you gamma, 2 phi is known, but we do not know what VSB is. VSB. That is equal to Vs minus Vb. Again, Vs is unknown. Vb though is it's the body which is connected to the lowest supply, which is VSS. So Vb is equal to VSS. VSS is minus 5 volts, so just watch your negative signs in this equation when you plug it in. So out of this equation, we do not know what Vt1 is, and we do not know what Vs is. Back to this one, the first one, we don't know Vs and we don't know Vt1. So same variables, we have two equations, two unknowns. If you solve this, it'll be a quadratic, and you'll have two results, but only one set of results will make sense. But you can solve these two equations and you will figure out what Vs equals, and you'll figure out what Vt1 equals. And once you know Vs, you can figure out what VGS is. VG1 minus VS1. If the gate's connected to 0, then VGS1 is equal to 0 minus VS1. VS1, you should get a negative value here for VS. Since the gate is at 0 and the supply is -5, you're going to be somewhere between 0 and -5 for this to operate correctly. And VT1 will be something greater than VTO because it is increased due to body effect. So it'll be greater than 0.7. So this was part 1. Part 2. Let's read that real quick. You need to figure out the minimum value of VCOM. That's the DC voltage that you apply to the gates. So this is a little tricky, but basically the same idea. You can't neglect body effect, but body effect will be a little bit different this time. It won't be the exact same value that you calculated earlier. It'll be slightly different. So to figure out the minimum value of VCOM, we basically need to figure out when does this current source M6 go into triode. If you remember from the last lab, there's a VDS min requirement of M6. So VDS 6, it has to be greater than VGS minus VT. And this guy's got source and body at the same terminal, so body effect isn't here. This will be around 2.5 volts minus 0.7 volts. Should be around 1.8 volts. So that tells you what the source voltage is of M1 and M2. So VS1 is equal to VS2 is VSS plus that VDS6 value. Okay, so minus 3.2 volts. That's as low as this node can go before M6 goes into triode. If you know the source voltage, then you can figure out what VT is. Right, just the body effect equation again, except you actually know the source voltage this time, so you can directly solve for VT1. Once you know VT1, you can plug it into the saturation equation. Okay, you know everything here now, except for VGS1. So solve for VGS1. And once you know VGS1, you can figure out what VG is by just substituting VGS1 is equal to VG1 minus VS1. You just solve for VG1 or VGS1. VS1 is the minus 3.2 volts that you calculated. You can solve for VG1. And VG1 in this scenario is equal to VCOM min, because it'll be the minimum voltage you can put on the gate that keeps M6 in saturation. If you go below this value, then the source voltage here will drop so low that this guy will be in triode, which we're trying to avoid. Okay, so part 3 is to calculate the differential mode gain, common mode gain, and common mode rejection ratio. And they give you all these equations in the text here on page 3 of the lab handout. So differential gain is equal to GM1 RO, oh, it says RO2, parallel RO4, parallel RL. RO1 and RO2 are the same, RO3 and RO4 are the same. It's just the NMOS and PMOS of the differential pair, 1 and 2 and 3 and 4. And it's the differential pair transconductance at the inputs that sets the gain of the amplifier. So GM, you can calculate from square root of 2 Kn prime W over L ID. Or don't forget ID is 2 milliamps here, since the 4 is divided between the two sides. So you can solve for that. RO is 1 over lambda ID. They tell you what lambda is for the NMOS and the PMOS. ID is 2 milliamps again. So you can solve all that for the differential gain. There is no load resistance in this case, so you can just ignore RL in this equation. RL equals infinity in this scenario. The next equation you need is for common mode gain. And that is approximately 1 over 2 GM3 RO6. It's the output resistance of the current source. So again, you can calculate GM based on these parameters, except GM3 is PMOS. So use KP prime in this case. ID is 2 milliamps again, and you can solve for RO the same way you did before. And the last piece is common mode rejection ratio, which is just the ratio of those two things we just calculated. 20 log base 10 of AD to ACM. All right, and that should be somewhere around 60 dB, if I remember correctly. That's about right. And that's it for the hand calculations. The rest of the pre-lab will be simulations with LT Spice.